Welcome to Tech with Kaushik. This is set 8 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 8. Question number 126. Let's go. The topic for this question is event-driven automation. A large enterprise manages thousands of Amazon EC2 instances. The cloud operations team relies on a dedicated Slack channel and a centralized email distribution list for critical operational alerts. A DevOps engineer has been tasked with ensuring that all scheduled EC2 maintenance notifications generated by AWS are automatically sent to both the Slack channel and the email distribution list. The alerts must dynamically include the EC2 instance's name and environment tags to help the team identify the affected workload. Which solution will meet these requirements most efficiently? Option A. Create an Amazon Event Bridge rule that filters for AWS health events related to EC2 maintenance. Target an AWS Lambda function that retrieves the instance tags via the EC2 API, formats the message, publishes it to an Amazon SNS topic for the email distribution list, and sends the same formatted message to the Slack incoming webhook. Option B. Configure an AWS config rule to monitor the state of EC2 instances. Set up an automated remediation action that triggers an AWS Lambda function to query AWS health, fetch tags, and send emails via Amazon SES. Option C. Integrate AWS Trusted Advisor with Amazon SNS. Subscribe an AWS Lambda function to the SNS topic that parses the Trusted Advisor maintenance checks, extracts the tags, and sends HTTP post requests to Slack. Option D. Create an Amazon CloudWatch alarm based on the status check failed metric for all instances. Configure the alarm to trigger an Amazon SNS topic that natively formats and routes the alerts to Slack and email. The answer here is option A. Create an Amazon Event Bridge rule that filters for AWS health events related to EC2 maintenance. Target an AWS Lambda function that retrieves the instance tags via the EC2 API, formats the message, publishes it to an Amazon SNS topic for the email distribution list, and sends the same formatted message to the Slack incoming webhook. Here's why. AWS Health publishes service events, including EC2 scheduled maintenance, to Event Bridge. Lambda is appropriate for enriching the event with EC2 tags and formatting the message. It can publish the email notification through SNS and post the enriched payload to the Slack incoming webhook, satisfying both delivery channels without polling. Let's quickly check the incorrect choices. B. AWS config evaluates resource configuration and compliance. It is not the primary event source for AWS scheduled EC2 maintenance. C. Trusted Advisor is not the direct event source for EC2 scheduled maintenance and adds an unnecessary indirection compared with AWS health events. D. Status check failed reports current instance health failures, not future AWS scheduled maintenance events. For AWS scheduled maintenance, route AWS health events through Event Bridge. Use Lambda when the notification requires tag enrichment or custom payload formatting. Question number 127. Scenario. A development team uses an AWS code pipeline workflow integrated with AWS Code Deploy to push application updates to an Amazon EC2 fleet. Recently, a faulty application dependency caused the Code Deploy phase to silently fail, and the team was unaware of the issue until customers reported it. The DevOps engineer must implement an automated notification system to alert the team immediately if a deployment fails. Which approach requires the least custom development overhead to meet this requirement? Choices. Option A. Enable AWS CloudTrail to log all code pipeline and Code Deploy API calls. Create an AWS Lambda function that parses the CloudTrail logs in Amazon S3 for failure codes and sends a notification to an Amazon SNS topic. Option B. Create Amazon Event Bridge rules that match the failed execution states for AWS Code Pipeline and AWS Code Deploy. Configure the rules to target an Amazon SNS topic that sends an email to the development team. Option C. Install the CloudWatch agent on all EC2 instances to monitor the Code Deploy agent logs. Create a CloudWatch metric filter for the word error and trigger an alarm that publishes to an Amazon SNS topic. Option D. Configure an AWS config rule to evaluate the operational status of code pipeline and code deploy. Use AWS Systems Manager automation to send a notification to stakeholders when a non-compliant state is detected. In this case, choose option B. Create Amazon Event Bridge rules that match the failed execution states for AWS Code Pipeline and AWS Code Deploy. Configure the rules to target an Amazon SNS topic that sends an email to the development team. This is the best choice because AWS Code Pipeline and AWS Code Deploy natively emit state change events, such as started, succeeded, failed, directly to Amazon Event Bridge. Creating Event Bridge rules to filter for failed states and target an Amazon SNS topic requires zero custom code, scales automatically, and operates in near real time. Now let's rule out the other options. A. Parsing CloudTrail logs from S3 via Lambda introduces significant latency, operational overhead, and custom code maintenance for something Event Bridge handles natively. C. Code deploy agent logs on the EC2 instance do not reflect pipeline-level failures and require heavy custom metric filter management. D. AWS config evaluates resource compliance state, not real-time operational execution failures of deployment pipelines. The main takeaway is always prefer Amazon Event Bridge for intercepting state changes and operational events from AWS developer tools over parsing CloudTrail logs or writing custom polling scripts. Next, question number 128. A legacy deployment process involves a developer manually compiling code locally, uploading a zip file to an Amazon S3 bucket, logging into an Amazon EC2 instance, running a script to clear an application cache, and finally extracting the zip file. The company wants to modernize this into a fully automated CI/CD pipeline that builds the artifact, deploys it to a fleet of instances, runs the cache clearing script, and rolls back if the deployment fails. Which combination of actions will construct this modernized pipeline? Choose 4. More than one answer may be correct. Options. Option A. Use AWS Code Build to pull the source code, compile the application, and store the resulting artifact in Amazon S3. Option B. Configure an AWS code pipeline workflow that uses a source code repository as the trigger and orchestrates the build and deployment stages. Option C. Place the cache clearing script inside the EC2 instance user data to ensure the cache is purged every time the instance processes a deployment. Option D. Use AWS Systems Manager run command to fetch the zip file from Amazon S3 and execute a bash script across the fleet to orchestrate the rollout. Option E. Use AWS Code Deploy to orchestrate the artifact deployment to the EC2 fleet, utilizing automatic rollback configurations on failure. Option F. Write a custom AWS Lambda function to listen for S3 object-created events, extract the zip file, and push the contents to the EC2 instances via SSH. Option G. Include the cache clearing script in the application source code and reference it in the application stop or before install hook of an AppSpec file. The correct answers are Option A. Use AWS Code Build to pull the source code, compile the application, and store the resulting artifact in Amazon S3. Option B. Configure an AWS code pipeline workflow that uses a source code repository as the trigger and orchestrates the build and deployment stages. Option E. Use AWS Code Deploy to orchestrate the artifact deployment to the EC2 fleet, utilizing automatic rollback configurations on failure. And Option G. Include the cache clearing script in the application source code and reference it in the application stop or before install hook of an AppSpec file. Let's look at the reasoning. Code pipeline orchestrates the source, build, and deploy stages. Code build compiles the application and produces the artifact. Code deploy deploys to the EC2 fleet and supports automatic rollback. The cache clearing script must be included in the revision and invoked from an AppSpec lifecycle hook, such as application stop or before install, so it runs on every deployment before the new files are installed. The other choices do not work because C. EC2 user data is associated with instance launch and is not the correct mechanism for a script that must run during every code deploy deployment. D. Systems Manager run command can execute fleet commands, but it does not replace code deploy's deployment lifecycle, revision tracking, and automatic rollback required here. F. a custom Lambda function that pushes files over SSH, duplicates managed CI/CD capabilities, and adds unnecessary custom operational logic. A helpful shortcut is this. For EC2 CI/CD, separate orchestration, build, and deployment concerns. Code pipeline plus code build plus code deploy, with per deployment host scripts defined in app spec lifecycle hooks. Question number 129. Let's go. Next, let's move into compliance automation. Scenario. A security auditing team requires that all Amazon Elastic Block Store, EBS, volumes created across the company's AWS account are encrypted at rest using AWS KMS. Since developers frequently provision new environments, the security team needs an automated solution to ensure compliance. If an unencrypted EBS volume is detected, the system should automatically remediate the issue without requiring manual intervention. Which solution will fulfill these requirements with the least operational overhead? Option A. Enable AWS CloudTrail to log EC2 create volume API calls. Use Amazon EventBridge to trigger an AWS Lambda function that encrypts the volume if it is unencrypted. Option B. Enable AWS config and configure a managed config rule to check for EBS encryption. Configure an automatic remediation action using an AWS Systems Manager automation document. Option C. Run Amazon Inspector assessments daily to detect unencrypted EBS volumes. Route the inspector findings to AWS Security Hub and use Lambda to force encryption. Option D. Use AWS Trusted Advisor to flag unencrypted volumes. Configure an Amazon EventBridge rule to intercept Trusted Advisor alerts and invoke an AWS Systems Manager document. The best choice is option B. Enable AWS config and configure a managed config rule to check for EBS encryption. Configure an automatic remediation action using an AWS Systems Manager automation document. This works because AWS config continuously monitors and records resource configurations. It provides an AWS managed rule specifically for checking if EBS volumes are encrypted. By linking an AWS Systems Manager automation document to the config rule, AWS natively and automatically remediates the non-compliant resource as soon as config flags it, resulting in the lowest possible operational overhead and no custom code. The remaining options can be eliminated because A. While EventBridge and Lambda can accomplish this, it requires writing, maintaining, and testing custom Python/Node.js code, which carries higher operational overhead than using native managed rules and documents. C. Amazon Inspector is a vulnerability management service focused on network exposures and software vulnerabilities inside instances, not primarily for configuration drift like EBS encryption. D. Trusted Advisor can report unencrypted volumes, but AWS config is specifically designed for continuous compliance tracking and native integration with SSM remediation actions. Here's a useful exam tip. For automated compliance remediation with the least overhead, pair AWS config managed rules with AWS Systems Manager, SSM, automation documents. Question number 130. Here's what is happening. A company's AWS organization structure includes a root container, an infrastructure organizational unit, OU, and a staging child OU. By default, the full AWS Access AWS Managed Service Control Policy, SCP, is attached to the root and all OUs. A DevOps engineer detaches the full AWS Access SCP from the staging OU. The engineer then attaches a new custom SCP to the staging OU that explicitly allows only the S3* and DynamoDB* actions. What is the effective consequence of this change for IAM principals operating in the AWS accounts under the staging OU? The choices are: Option A. The principals will only be able to perform Amazon S3 and Amazon DynamoDB actions, provided their IAM policies also grant them these permissions. Access to all other AWS services will be denied. Option B. The principals will retain access to all AWS services because the full AWS access policy is still attached at the root level, which supersedes the child OU policies. Option C. The principals will be granted full administrative access to Amazon S3 and Amazon DynamoDB immediately, regardless of what their local IAM policies allow. Option D. The principals will be explicitly denied access to Amazon S3 and Amazon DynamoDB, while retaining access to all other services governed by the root SCP. Go with option A. The principals will only be able to perform Amazon S3 and Amazon DynamoDB actions, provided their IAM policies also grant them these permissions. Access to all other AWS services will be denied. Service control policies, SCPs, do not grant permissions. They act as a filter or boundary. For an action to be allowed, it must be explicitly allowed by an SCP at every level of the organization hierarchy, root, OU, and account, and explicitly allowed by the IAM principal's identity-based policy. By removing full AWS access and attaching a policy that only allows S3 and DynamoDB at the staging OU level, the SCP effectively filters out all other AWS services for accounts in that OU, regardless of what the root allows. Here's why the alternatives are not suitable. B. SCPs must allow the action at every level in the path. If an OU SCP restricts access, the root SCP cannot override it to grant broader access. C. SCPs never grant permissions by themselves. The principal still needs an IAM policy granting the specific permissions. D. The custom SCP explicitly allowed S3 and DynamoDB, which acts as an allow list. Because all other services are not explicitly allowed at the staging OU level, an implicit deny is evaluated for them. Keep this point in mind for the exam. In AWS organizations, an implicit deny anywhere in the SCP hierarchy blocks access. An SCP must allow an action at every node from the root to the account for the IAM policy to take effect. Question number 131. The focus now shifts to security automation. Scenario. A financial services company maintains over 100 AWS accounts in an AWS organization. A central cloud governance team requires near real-time visibility into AWS service misconfigurations, such as unrestricted security groups or unencrypted databases. When a misconfiguration is detected, it must be automatically remediated within 15 minutes. The governance team also requires a single, unified dashboard to view the compliance status of all accounts across the organization. Which solution meets these requirements with the least custom development effort? Options. Option A. Enable AWS CloudTrail in all accounts and stream logs to Amazon CloudWatch logs. Use CloudWatch metric filters to detect misconfigurations and trigger Amazon Event Bridge rules. Route events to an AWS Lambda function for remediation and push metrics to a centralized Amazon QuickSight dashboard. Option B. Configure AWS config to record resources in all accounts. Enable AWS Security Hub across the organization and deploy security standards. Configure custom or managed AWS config rules for automatic remediation via AWS Systems Manager automation. Use the Security Hub delegated administrator account for the unified dashboard. Option C. Enable AWS Control Tower to manage the multi-account environment. Create preventative service control policies, SCPs, to block misconfigurations. Use AWS config aggregators to build a centralized dashboard in the management account. Rely on SCPs rather than reactive remediation. Option D. Use AWS Cloud Formation Stack sets to deploy a custom AWS Lambda function to all accounts. The Lambda function runs every 10 minutes to scan resource states and remediate issues. The function writes compliance records to a centralized Amazon DynamoDB table backed by an Amazon API Gateway dashboard. The right response is option B. Configure AWS config to record resources in all accounts. Enable AWS Security Hub across the organization and deploy security standards. Configure custom or managed AWS config rules for automatic remediation via AWS Systems Manager automation. Use the Security Hub delegated administrator account for the unified dashboard. The main reason is AWS Security Hub natively integrates with AWS config and AWS organizations to aggregate compliance findings across multiple accounts into a single, unified dashboard in a delegated administrator account. AWS config rules can be configured with automated remediation using AWS Systems Manager automation documents, fulfilling the 15-minute remediation requirement with entirely native, managed services and minimal custom development. A. Building custom CloudWatch metric filters, event bridge rules, custom Lambda functions for remediation, and a QuickSight dashboard requires significant, ongoing custom development effort. C. Service control policies, SCPs, are preventative guardrails but cannot remediate existing misconfigured resources. Furthermore, config aggregators provide a dashboard, but Security Hub is the best practice service for unified security and compliance posture. D. Deploying custom Lambda functions via stack sets to run on cron schedules is highly inefficient, requires maintaining custom code, and does not provide a native unified dashboard out of the box. Exam tip. When asked for multi-account security posture monitoring with centralized dashboards and automated remediation with the least overhead, look for AWS Security Hub integrated with AWS Config and Systems Manager automation. Here comes question number 132. A company recently deployed AWS IAM Identity Center, AWS Single Sign-On, to centralize access management for its multi-account environment. The company uses an external SAML 2.0 identity provider, IDP, such as Okta, as its corporate directory. A DevOps engineer needs to ensure that when an employee joins a specific group in the corporate directory, their user identity and group membership are automatically synchronized to IAM Identity Center without manual intervention. Which configuration step should the engineer perform to enable this automated synchronization? Here are the options. Choice A. Set the IAM Identity Center identity source to the external IDP. Enable automatic provisioning using the System for Cross-Domain Identity Management, SCIM, version 2.0 protocol, and configure the IDP with the SCIM endpoint. Choice B. Set the IAM Identity Center identity source to AWS Directory Service. Configure an inbound directory trust to sync groups and users using the LDAP protocol. Choice C. Configure an Active Directory Connector, AD connector, in the management account. Use AWS Lambda to poll the external IDP AP is and push user updates to IAM Identity Center via SAML assertions. Choice D. Set the IAM Identity Center identity source to the external IDP. Rely entirely on SAML 2.0 assertions during user login to dynamically create users and group memberships just in time. Go with option A. Set the IAM Identity Center identity source to the external IDP. Enable automatic provisioning using the System for Cross-Domain Identity Management, SCIM, version 2.0 protocol, and configure the IDP with the SCIM endpoint. Here's why. The SCIM, System for Cross-Domain Identity Management, protocol is an open standard designed specifically to automate the exchange of user identity information between identity domains or IT systems. By enabling SCIM in AWS IAM Identity Center and configuring it in the external IDP, user creations, updates, and group membership changes are synced automatically in the background. Let's quickly check the incorrect choices. B. AWS Directory Service uses LDAP/Active Directory Trusts, not standard web-based identity providers. SCIM is the standard for modern external IDPs. C. Writing custom Lambda polling scripts to AD connector is entirely unnecessary since IAM Identity Center natively supports SCIM. D. SAML 2.0 provides authentication and can pass attributes dynamically during login, just-in-time provisioning, but it only syncs data when the user logs in. It does not automatically synchronize group memberships in the background before a login event. For automated, background user and group synchronization between an external identity provider, Okta, Azure AD, and AWS IAM Identity Center, always choose SCIM version 2.0. Next, question number 133. We're moving on to artifact management. A DevOps engineer is troubleshooting an AWS code build project. The pipeline successfully compiles a container image, but fails during the push phase when attempting to upload the image to an Amazon Elastic Container Registry, Amazon ECR, private repository. The code build IAM service role already has full ECR permissions attached, and the ECR repository exists in the same AWS region. The build spec.yml file executes standard Docker commands. What must the engineer add to the pipeline configuration to resolve the access failure? Choices. Option A. Update the ECR repository policy to allow anonymous pushes, since code build instances operate outside of the customer's VPC. Option B. Store an IAM user's static AWS access key ID and secret access key in AWS Secrets Manager and expose them as environment variables in code build for the Docker daemon to use. Option C. Modify the build spec.yml file to execute the AWS ECR get login password command to retrieve an authentication token and pass the token to the Docker login command before pushing the image. Option D. Add the AWS CLI AWS STS assume role command to the build spec.yml file to assume a cross-account role, as ECR requires temporary credentials explicitly requested during the build phase. The answer here is option C. Modify the build spec.yml file to execute the AWS ECR get login password command to retrieve an authentication token and pass the token to the Docker login command before pushing the image. This is the best choice because even if an IAM role has permissions to push to Amazon ECR, the native Docker CLI, Docker run, Docker push does not inherently understand AWS IAM authorization. You must exchange the IAM credentials, which CodeBuild has automatically via its service role, for a temporary Docker authentication token using the AWS CLI command AWS ECR get login password and pipe that to Docker login. Now let's rule out the other options. A. Allowing anonymous pushes to an ECR private repository is a massive security risk and fundamentally circumvents proper IAM authentication. B. Injecting static, long-lived AWS IAM access keys as environment variables is an insecure anti-pattern. CodeBuild securely provides temporary credentials to the build environment automatically. D. You do not need to assume a cross-account role if the repository is in the same account/region and the CodeBuild service role already has permissions. You just need to translate those permissions into a Docker login token. The main takeaway is whenever standard Docker CLI commands interact with Amazon ECR, you must authenticate the Docker client first using AWS ECR get login password Docker login. Next, question number 134. Scenario. A development team is migrating a legacy C++ application to a modern CI/CD pipeline on AWS. Building the application artifact requires an older, highly customized compiler toolchain that takes several hours to manually configure on a base operating system. The team needs to automate the build process using AWS CodeBuild and output the resulting deployable artifact to Amazon S3. Which approach fulfills this requirement with the most operational efficiency and consistency? Option A. Use AWS Systems Manager State Manager to keep the custom compiler toolchain installed on a fleet of long-lived Amazon EC2 build hosts. Configure the pipeline to invoke build scripts on those hosts and upload the artifact to Amazon S3. Option B. Launch an Amazon EC2 instance, manually install and verify the custom toolchain, and configure an AWS Code Deploy agent on it. Trigger Code Deploy from the pipeline to build the artifact locally on the instance. Option C. Create a custom Docker image containing the required older toolchain and all dependencies. Push this image to an Amazon ECR repository. Configure the AWS CodeBuild project environment to use this custom Docker image. Option D. Configure the AWS CodeBuild project to use a standard Amazon Linux 2 managed image. Add a bash script to the pre-build phase of the build spec.yml to download, compile, and install the legacy toolchain before every build. In this case, choose option C. Create a custom Docker image containing the required older toolchain and all dependencies. Push this image to an Amazon ECR repository. Configure the AWS CodeBuild project environment to use this custom Docker image. Let's look at the reasoning. A custom Docker image packages the legacy compiler and dependencies once, producing a repeatable CodeBuild environment on every run. Hosting the image in Amazon ECR avoids reinstalling a toolchain that takes hours to configure while preserving managed, ephemeral build execution and consistent artifacts. The other choices do not work because A. Long-lived EC2 build hosts require ongoing patching and configuration state management and lose much of the operational benefit of managed, repeatable code build environments. B. A manually maintained EC2 build server is not a reproducible managed build environment and adds server lifecycle and drift management. D. Reinstalling a multi-hour legacy toolchain during every build greatly increases build time and makes the pipeline less efficient. A helpful shortcut is this. When CodeBuild needs a complex or legacy toolchain, bake the toolchain into a custom container image in ECR instead of rebuilding the environment on every run. Next up is question number 135. This question takes us into automated testing. Consider this situation. A financial organization requires strict data validation testing before application updates are deployed to production. The production environment uses an Amazon Aurora Postgres QL cluster. The DevOps team needs a CI/CD pipeline stage that runs destructive integration tests against an exact, up-to-date copy of the production database schema and data. The testing process must not impact the performance or availability of the live production database. Which solution meets these testing requirements with the highest performance and lowest operational overhead? Choice A. Create an automated script in AWS code build that initiates an Aurora database clone of the production cluster. Run the integration tests against the newly created clone and delete the clone once tests conclude. Choice B. Configure the pipeline to take a manual snapshot of the Aurora production cluster. Use AWS CloudFormation to deploy a new standard Amazon RDS instance from the snapshot, run the tests, and tear down the stack. Choice C. Modify the application deployment to point to the production Aurora replica reader node. Execute the destructive integration tests against the read replica to isolate the write workload from primary users. Choice D. Use AWS Database Migration Service, AWS DMS, in continuous replication mode to sync production data to an Amazon DynamoDB table. Run the application tests against the DynamoDB table. The best choice is option A. Create an automated script in AWS code build that initiates an Aurora database clone of the production cluster. Run the integration tests against the newly created clone and delete the clone once tests conclude. This works because Aurora cloning uses copy-on-write storage, so a clone can be created quickly without making a full physical copy of the source cluster. At creation, the clone has the source cluster's data, while subsequent changes are isolated. This makes it well suited to destructive integration testing that must not modify the live production database. The remaining options can be eliminated because B. An Aurora cluster snapshot cannot be restored as a standard non-Aurora RDS Postgres QL instance, and a snapshot/restore workflow adds more provisioning overhead than an Aurora clone. C. Aurora replicas are read-only for application writes, so they cannot support destructive write-based integration tests. D. Replicating Postgres QL data into DynamoDB changes the database model and cannot provide an exact Postgres QL test target without application redesign. Here's a useful exam tip. Use Aurora cloning when a test stage needs a fast, isolated copy of an Aurora production dataset. Copy-on-write avoids a full data copy at clone creation. Question number 136. A company runs a heavily trafficked web application spanning hundreds of Amazon EC2 instances within a single VPC. Amazon Guard Duty is enabled and frequently detects instances communicating with known malicious IP addresses, command and control servers. The security team requires a completely automated remediation pipeline that blocks traffic to and from these newly identified malicious IP addresses at the VPC boundary level, protecting all current and future resources in the VPC. Which solution will automatically enforce this network block across the entire VPC? Options. Option A. Route all VPC traffic through AWS Network Firewall. Use an Amazon Event Bridge rule to capture Guard Duty findings and trigger an AWS Lambda function that updates an AWS Network Firewall rule group to drop traffic from the malicious IP. Option B. Create an AWS Lambda function triggered by Guard Duty findings. Have the Lambda function iterate through all EC2 instances in the VPC and update their individual security groups to explicitly deny the malicious IP address. Option C. Deploy AWS WAF on the application load balancer. Use an Amazon Event Bridge rule that reacts to Guard Duty findings and invokes an AWS Lambda function to add the malicious IP to an AWS WAF IP set block list. Option D. Use an Amazon Event Bridge rule to capture Guard Duty findings. Trigger an AWS Systems Manager automation document that pushes a Guard Duty suppression rule via the API, automatically dropping malicious packets at the hypervisor level. The right response is option A. Route all VPC traffic through AWS Network Firewall. Use an Amazon Event Bridge rule to capture Guard Duty findings and trigger an AWS Lambda function that updates an AWS Network Firewall rule group to drop traffic from the malicious IP. AWS Network Firewall provides VPC-level, highly scalable network protection. By routing traffic through the firewall, you establish a centralized choke point. When Guard Duty detects a malicious IP, the finding is sent to Event Bridge. Event bridge triggers a Lambda function that dynamically adds the IP to a deny rule in the network firewall rule group. This instantly protects all existing and future EC2 instances across the entire VPC without managing individual instance configurations. Here's why the alternatives are not suitable. B. Iterating through hundreds of EC2 instances to update individual security groups is slow, prone to API throttling limits, and does not protect instances launched immediately after the script runs. C. AWS WAF protects application layer endpoints, like ALBs and API gateway, against HTTP/HTTPS attacks. It does not block general VPC traffic, for example, raw TCP/UDP outbound traffic to command and control servers from EC2 instances. D. Guard duty suppression rules simply hide the alerts in the guard duty console. They do not alter network routing or drop packets at the hypervisor level. Keep this point in mind for the exam. To centrally block IP traffic across an entire VPC automatically, integrate Amazon Guard Duty findings via EventBridge to update AWS network firewall rules. Question number 137. Let's go. Scenario. A software company uses AWS code commit in the US East 1 region as its primary source control repository. To satisfy a strict disaster recovery mandate, the company must maintain a synchronized backup of the repository in the US West 2 region. In the event of a total regional outage in US East 1, developers must be able to update their local Git remotes and immediately resume committing code to the repository in US West 2. Which architecture will fulfill this requirement automatically? Choices. Option A. Enable Amazon S3 cross-region replication, CRR, on the underlying S3 bucket that code commit uses to store Git objects, ensuring that US West 2 has an identical block-level copy of the repository. Option B. Set up an Amazon event bridge rule in US East 1 that triggers on code commit repository state changes. Target an AWS code build project configured to perform a Git clone from the primary repository and a Git push, mirror to a secondary code commit repository in US West 2. Option C. Create an AWS code pipeline with a cross-region action. Configure the pipeline to automatically package the source code into a zip file upon every commit and upload it to an AWS code artifact repository in US West 2. Option D. Configure AWS Cloud 9 environments for all developers in US West 2. Connect the IDEs to the primary repository and use a continuous syncing script in Cloud 9 to replicate changes to a secondary code commit repository. Go with option B. Set up an Amazon event bridge rule in US East 1 that triggers on code commit repository state changes. Target an AWS code build project configured to perform a Git clone from the primary repository and a Git push, mirror to a secondary code commit repository in US West 2. The main reason is AWS code commit does not have a native, fully managed cross-region replication toggle. The AWS prescribed architecture for replicating a code commit repository involves using Amazon Event Bridge to detect repository reference updates, commits, branches, tags, and triggering an AWS code build project. The code build project performs a Git push, mirror to a backup code commit repository in another region, preserving the entire Git history and branch structure. A. S3 cross-region replication on the underlying buckets managed by AWS for code commit is not exposed to the customer. You cannot configure S3 CRR for managed code commit storage. C. Code artifact is a package manager for NPM, Maven, PyPI artifacts, not a Git source code repository. Furthermore, zipping source code destroys the Git history, making it useless for developers to simply switch remotes and continue committing. D. Relying on IDEs, AWS Cloud 9, to perform continuous syncing is an anti-pattern. It depends on user environments being active and introduces massive synchronization conflicts. Exam tip. To replicate an AWS code commit repository to another region, use EventBridge to trigger a code build project that executes Git push, mirror. Next, question number 138. An AWS Lambda function integrates with a third-party payment gateway. The API keys for the payment gateway are stored in AWS Secrets Manager and are encrypted using the default AWS managed key, AWS/Secrets Manager. A DevOps engineer is conducting a security review and determines that the principle of least privilege is not being met because other principals in the account could theoretically be granted access to the default managed key. The engineer must ensure that strictly only the Lambda function's IAM execution role can decrypt this specific secret. Which combination of steps must the engineer take to enforce this restriction? Choose 2. Identify all valid responses. Option A. Create a customer-managed key, CMK, in AWS KMS. Configure the key policy to grant the KMS decrypt action exclusively to the Lambda function's IAM execution role. Option B. Re-encrypt the API key secret in AWS Secrets Manager using the newly created customer-managed key, CMK. Option C. Edit the default AWS/Secrets Manager KMS key policy to explicitly deny the KMS decrypt action to all principals except the Lambda function's IAM execution role. Option D. Attach an identity-based IAM policy to the Lambda execution role that explicitly denies the KMS encrypt action on all AWS KMS keys. E. Move the API keys from AWS Secrets Manager to AWS Systems Manager Parameter Store and encrypt them using the default AWS/SSM KMS key. The answers that work here are Option A. Create a customer-managed key, CMK, in AWS KMS. Configure the key policy to grant the KMS decrypt action exclusively to the Lambda function's IAM execution role, and Option B. Re-encrypt the API key secret in AWS Secrets Manager using the newly created customer-managed key, CMK. Here's why. AWS managed keys, like AWS/Secrets Manager, have key policies that cannot be modified by the customer. Because the policy cannot be restricted, any principal with generic KMS permissions might theoretically decrypt it. To enforce strict least privilege, the engineer must create a customer-managed key, CMK. Configure the key policy to allow only the specific Lambda IAM role to use it for decryption, and then configure Secrets Manager to use this new CMK for that specific secret. Let's quickly check the incorrect choices. C. You cannot edit the key policy of an AWS managed key. D. Denying KMS encrypt on the Lambda role does not prevent other principals in the account from decrypting the secret, which is the core security concern described in the scenario. E. Moving the secret to parameter store and using the default AWS/SSM key does not solve the problem, as default managed keys still cannot have their key policies edited to enforce strict least privilege. To tightly control who can use an encryption key via a key policy, you must use an AWS KMS customer managed key, CMK. You cannot modify policies on default AWS managed keys. Question number 139. We're moving on to CloudWatch alarms. Scenario. A company runs asynchronous batch processing jobs on an Amazon EC2 instance. The company wants to terminate the instance automatically to save costs if it remains idle. A DevOps engineer determines that the instance is idle if the CPU utilization metric drops below 10% for at least 20 minutes within a 30-minute evaluation window. Occasionally, the EC2 instance reboots, causing a temporary gap in CloudWatch metric data. The engineer must ensure that these brief periods of missing data do not accidentally trigger the termination alarm. The metric is collected with a 5-minute period. How should the DevOps engineer configure the CloudWatch alarm to meet these exact requirements? Options. Option A. Set the evaluation period to 5 minutes. Set data points to alarm to 6 out of 6. Configure the alarm to treat missing data as breaching. Add an EC2 action to terminate the instance when in alarm state. Option B. Set the metric period to 5 minutes, evaluation periods to 6, and data points to alarm to 4. Configure treat missing data as not breaching. Add an EC2 action to terminate the instance when the alarm is in the alarm state. Option C. Set the evaluation period to 5 minutes. Set data points to alarm to 4 out of 6. Configure the alarm to treat missing data as breaching. Add an AWS Systems Manager runbook action to terminate the instance. Option D. Set the evaluation period to 30 minutes. Set data points to alarm to 1 out of 1. Configure the alarm to treat missing data as ignore. Add an EC2 action to stop the instance when in alarm state. The best choice is Option B. Set the metric period to 5 minutes, evaluation periods to 6, and data points to alarm to 4. Configure treat missing data as not breaching. Add an EC2 action to terminate the instance when the alarm is in the alarm state. This is the best choice because a 30-minute window with a 5-minute metric period contains 6 evaluation periods. Requiring at least 20 minutes below the threshold means 4 of those 6 data points must breach. Treating missing data as not breaching prevents reboot-related gaps from being counted as breaches, and a native EC2 terminate action can run when the alarm enters alarm. Now let's rule out the other options. A. Requiring 6 of 6 breaching data points means 30 minutes of low CPU, and treating missing data as breaching can create a false termination during a metric gap. C. The 4 of 6 count is correct, but treating missing data as breaching violates the requirement to avoid false termination during reboot gaps. D. A single 30-minute aggregate cannot represent the required 4 of 6 5-minute data point logic, and stopping is not the requested termination action. The main takeaway is for CloudWatch M out of N alarms. Data points to alarm is M and evaluation periods is N. Use not breaching when missing data points must not count toward the alarm threshold. Question number 140. Let's go. A cloud governance team manages an AWS organization containing 200 member accounts. The team has authored a Python script designed to run in AWS Lambda. The script scans for and deletes unattached Amazon Elastic Block Store, EBS, snapshots older than 30 days to reduce storage costs. The team requires this Lambda function to execute automatically at midnight every day within every member account. What is the most operationally efficient way to deploy and schedule this automation across the entire organization? Choices. Option A. Create an AWS CloudFormation template that defines the Lambda function and an Amazon Event Bridge scheduled rule. Use AWS CloudFormation stack sets from the organization's delegated administrator account to deploy the template to all member accounts. Option B. Package the Lambda function into an AWS code deploy application. Use a centralized AWS code pipeline in the management account to assume IAM roles in each member account and orchestrate the Lambda deployment. Option C. Create an Amazon Event Bridge scheduled rule in the management account. Configure the rule to directly invoke the Lambda function in each of the 200 member accounts by adding 200 distinct cross-account targets to the single rule. Option D. Deploy the Lambda function in the management account only. Write a custom bash script that uses the AWS CLI to iterate through all 200 member accounts, assume a role, and trigger the function synchronously. The answer here is option A. Create an AWS CloudFormation template that defines the Lambda function and an Amazon Event Bridge scheduled rule. Use AWS CloudFormation stack sets from the organization's delegated administrator account to deploy the template to all member accounts. Let's look at the reasoning. AWS CloudFormation stack sets enables you to deploy infrastructure and code, like Lambda functions and Event Bridge rules, across multiple AWS accounts and regions from a single management or delegated administrator account. By deploying the Lambda function and its localized Event Bridge schedule trigger directly into each member account, the function executes autonomously and securely without cross-account role assumption complexities. The other choices do not work because B. Code pipeline and code deploy are designed for application deployments. Assuming roles dynamically across 200 accounts in a single pipeline is complex, brittle, and not a standard pattern for simple infrastructure automation. C. An Event Bridge rule in the management account cannot seamlessly invoke Lambda functions in 200 member accounts without configuring 200 cross-account resource policies on the target Lambdas and maintaining the rule targets manually as accounts are added/removed. D. Running a centralized bash script iterating over 200 accounts synchronously is an operational nightmare. It suffers from network timeouts, API throttling, and lacks native error handling and scale. A helpful shortcut is this. To deploy serverless automation scripts and their triggers across hundreds of AWS accounts in an AWS organization, use AWS CloudFormation stack sets. Let's continue with question number 141. Next, let's move into deployment strategies. Let's start with the scenario. A DevOps engineer is configuring an AWS code deploy in place deployment pipeline for an application hosted on Amazon EC2 instances. The instances run a custom third-party monitoring agent that locks application log files. If the code deploy agent attempts to overwrite the application files while the monitoring agent is running, the deployment fails. The DevOps engineer needs to ensure a script runs to safely stop the custom monitoring agent before the new application files are copied to the server during the deployment process. Which lifecycle event hook in the appspec.yml file should the engineer use to execute this script? Let's compare the available options. Option A is before allow traffic. Option B is application stop. Option C is after install. Option D is validate service. In this case, choose option B, application stop. This works because in the AWS code deploy lifecycle for an in-place deployment, the application stop hook is one of the very first events to run. It executes on the existing application instance before the download bundle step, which pulls the new artifact, and the before install and install steps, which copy files to the server. Therefore, shutting down the monitoring agent and application stop ensures file locks are released before code deploy attempts to overwrite the files. The remaining options can be eliminated because A, before allow traffic is primarily used in blue/green deployments on the replacement instances. For an in-place deployment, traffic routing hooks are typically used when integrated with an ALB, but they occur long after the files are already installed. C, after install occurs after code deploy has already copied the new application files to the server. If the files were locked, the deployment would have already failed at the install phase. D, validate service is the final hook used to check application health after it has been started. It runs after all files have been installed. Here's a useful exam tip. In AWS code deploy, to stop services or release file locks before new files are copied to the instance, execute scripts in the application stop or before install hooks of the appspec file. Now for question number 142. Here's the scenario. A development team maintains a Java application that is built and tested using AWS Code Build within an AWS Code Pipeline workflow. The engineering manager wants to easily view unit test pass/fail metrics, test duration, and detailed error messages directly within the AWS Management Console without having to download or manually parse raw log files from S3. How should the DevOps team fulfill this requirement natively in AWS? Review the options. Option A. Integrate Amazon Code Guru Reviewer into the code pipeline test stage. Configure the build environment to output tests in HTML format and pass the output to Code Guru for console rendering. Option B. Configure the Java testing framework to output results in JUnit XML format. Create an AWS Code Build report group and update the build spec.yml to specify the location of the XML files under the report sequence. Option C. Create an Amazon Event Bridge rule that intercepts code build state changes. Trigger an AWS Lambda function that extracts test results and publishes them as custom Amazon CloudWatch metrics viewable on a dashboard. Option D. Configure the pipeline to output CUCUMBRJS1 format files to an AWS Code Artifact repository. Use the Code Artifact console to visualize the test hierarchies and failure rates. The right response is option B. Configure the Java testing framework to output results in JUnit XML format. Create an AWS Code Build report group and update the build spec.yml to specify the location of the XML files under the report sequence. AWS Code Build features a native test reports capability via report groups. When a testing framework outputs results in standard formats, like JUnit XML or Cucumber.json, and those files are referenced in the reports section of the build spec.yml, Code Build automatically parses them. The results, including pass/fail rates, durations, and specific test case errors, are visualized natively directly within the AWS Code Build console. Here's why the alternatives are not suitable. A. Amazon Code Guru Reviewer is a machine learning tool that analyzes source code for vulnerabilities and best practice violations. It does not render or visualize dynamic unit test execution reports. C. While EventBridge and custom Lambda functions could technically parse data and push custom metrics to CloudWatch, it requires significant custom development for something Code Build does natively. D. A AWS Code Artifact is a secure package repository for storing dependencies, like Maven or NPM packages. It does not visualize test execution reports. Keep this point in mind for the exam. To visualize unit test execution results natively in AWS without custom code, configure your tests to output JUnit XML and use AWS Code Build report groups. Question number 143. Let's go. The focus now shifts to organizations and SCPs. A company recently acquired a startup. The startup's existing standalone AWS account was invited to join the parent company's AWS organization, and the invitation was accepted. A cloud administrator in the parent company's management account attempts to troubleshoot a resource in the newly joined member account by assuming the organization account access role via the AWS management console. The console returns an access denied error indicating the role cannot be assumed. What is the most likely cause of this issue, and how should it be resolved? Choices. Option A. The organization account access role is not automatically created for accounts that join via invitation. The administrator must log in directly to the startup's account using root or local IAM credentials, manually create the role, and configure the trust policy to allow the management account. Option B. The service control policy, SCP, attached to the startup's account is implicitly denying cross-account trust. The administrator must attach the default SCP from the organizational unit and apply a custom role assumption policy. Option C. The administrator's IAM user in the management account lacks the STS, assume role permission. An inline policy must be added to the IAM user granting permission to assume the newly created role. Option D. The startup's AWS account is still pending verification by AWS support. The administrator must wait 24 hours for the organization hierarchy to fully propagate before role assumption is enabled. The right response is option A. The organization account access role is not automatically created for accounts that join via invitation. The administrator must log in directly to the startup's account using root or local IAM credentials, manually create the role, and configure the trust policy to allow the management account. The main reason is when an AWS account is created from within AWS organizations, AWS automatically provisions the organization account access role in the new account, granting the management account administrative access. However, when an existing standalone account is invited to join the organization, this role is not created automatically. It must be manually provisioned by an administrator in the invited account before cross-account assumption will work. B. SCPs do not inherently block cross-account trust unless explicitly authored to do so, and the default behavior is lack of the role itself, not an SCP block. C. By default, users in the management account with administrator access already have STS, assume role permissions. The failure is due to the target role not existing in the member account. D. There is number 24-hour verification waiting period for role assumption. Once an invitation is accepted, organizational features are active immediately. Exam tip. Accounts invited to AWS organizations do not get the organization account access role automatically. It must be created manually. Next, question number 144. Scenario. An AWS Lambda function is configured to process records from an Amazon DynamoDB stream in batches of 100. If the Lambda function encounters a malformed record, it throws an error. The event source mapping is configured with an Amazon SQSQ as its on-failure destination. During testing, a developer notices that when one malformed record causes the invocation to fail, all 100 records in the batch are retried together until the retry policy is exhausted. Lambda then discards the failed batch and sends an invocation record describing that failed batch to the SQS destination. Valid records are therefore retried unnecessarily, and the failure record identifies the entire failed batch instead of isolating the malformed record. How can the DevOps engineer configure the Lambda event source mapping to isolate the malformed record while allowing valid records to complete successfully? Option A. Decrease the maximum age of record setting on the event source mapping to force immediate expiration of failed items. Option B. Enable the bisect batch on function error setting on the event source mapping to recursively split the failed batch until the specific failing record is isolated. Option C. Increase the maximum retry attempts on the Lambda function's asynchronous invocation configuration to allow more time for transient errors to resolve. Option D. Decrease the batch size from 100 to 1 to ensure records are only processed and failed individually. Go with option B. Enable the bisect batch on function error setting on the event source mapping to recursively split the failed batch until the specific failing record is isolated. Here's why. For DynamoDB streams, bisect batch on function error recursively splits a failed batch into smaller batches. Successful halves can advance, while failing halves are split again until the problematic record is isolated. If retries are later exhausted, the on-failure destination receives an invocation record describing the smallest failed batch rather than the original 100 record batch. Let's quickly check the incorrect choices. A. Reducing maximum record age only causes failed records to expire sooner. It does not isolate a bad record from otherwise valid records in the batch. C. The asynchronous invocation retry configuration is not the control used for DynamoDB stream event source mappings, and more retries would not isolate a deterministic malformed record. D. A batch size of 1 would isolate every record but sacrifices batching efficiency. Bisect on error provides isolation only when failures occur. For Kinesis or DynamoDB streams, bisect batch on function error isolates failing records without forcing batch size 1. SQS/SNS on failure destinations receive failure metadata, not the original record payload. Question number 145. This question takes us into CloudWatch alarms. A company uses an application load balancer, ALB, to route traffic to a fleet of microservices. The DevOps team tracks the target response time metric in Amazon CloudWatch. Traffic patterns fluctuate significantly depending on the time of day and day of the week, making it difficult to set a static threshold for high latency. The team wants to receive an automated notification only when the response time exhibits abnormal behavior relative to historical baseline trends. How should the DevOps engineer implement this monitoring requirement? Options. Option A. Enable CloudWatch anomaly detection on the target response time metric. Create a CloudWatch alarm based on the anomaly detection band, and configure the alarm to send a notification via Amazon SNS when the metric exits the expected band. Option B. Stream ALB access logs to Amazon Kinesis data firehose. Use an AWS Lambda function to calculate average response times every minute, compare against an Amazon DynamoDB historical table, and trigger Amazon SNS if an anomaly is found. Option C. Create a standard CloudWatch alarm with a static threshold set to the highest recorded historical peak. Add an AWS Systems Manager automation action to dynamically adjust the threshold via a cron job schedule. Option D. Subscribe an AWS Lambda function directly to the CloudWatch log group containing the ALB access logs. Configure the Lambda function to invoke an Amazon SageMaker endpoint for real-time inference and send an SNS alert. The best choice is Option A. Enable CloudWatch anomaly detection on the target response time metric. Create a CloudWatch alarm based on the anomaly detection band, and configure the alarm to send a notification via Amazon SNS when the metric exits the expected band. This is the best choice because Amazon CloudWatch anomaly detection applies machine learning algorithms to continuously analyze metrics and determine normal baselines over time. It automatically accounts for cyclical fluctuations, like time of day or day of week. Creating an alarm based on an anomaly detection band ensures alerts are only triggered when the metric genuinely deviates from its expected historical pattern, satisfying the requirement perfectly using native features. Now let's rule out the other options. B. Building a custom pipeline with Kinesis, Lambda, and DynamoDB to calculate baselines requires massive engineering overhead when CloudWatch provides this exact capability out of the box. C. Adjusting static thresholds via cron jobs is inaccurate, rigid, and does not dynamically react to true anomalies, but rather shifts a hard-coded value on a schedule. D. Using Lambda and SageMaker for simple metric anomaly detection introduces unnecessary cost, complexity, and architectural overhead compared to native CloudWatch features. The main takeaway is for metrics that exhibit cyclical or predictable fluctuations where static thresholds cause false alarms. Use CloudWatch anomaly detection to establish baseline bands dynamically. You have completed Set 8 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.